Michael Ingram. I'm a principal engineer at the National Renewable Energy Laboratory. I've been there about 7.5, 8 years and work in power system engineering, working primarily in resilience topics, power system engineering, interconnection, connecting distributed energy resources to the distribution grid, the issues associated with that, both on the technical side and the policy side. Started out my career at NREL in cybersecurity, cyber physical security. I worked there for a couple of years and transitioned into more traditional role, if you will, at NREL, working in power systems. I had the opportunity to work with NASA and Department of Defense, several other agencies in the federal government, and a little bit of international work in those spaces. Before joining NREL, I was at a large southern utility in the U.S., the Tennessee Valley Authority. You might have heard of it. I worked there about 28 years in substation and transmission engineering, worked in river system operations and environment, and then worked my way up into management before retiring from there and coming to work at NREL. Well, with respect to Rascal Flatts and Tom Cochrane, I would say the grid is a highway. If you know that song that I'm leveraging there, but it depends on where you are. If you're on the bulk power system, it's kind of like an interstate highway. But as you move closer to the consumer, it gets more like your local street. You've got issues similar to those. You've got potholes, you've got construction, you've got maintenance issues, you've got things like that as you get closer. And the amount of traffic, amount of congestion that it can handle changes depending on where you are on the grid, where you are on the highway. When people say inefficiencies, they think about losses. And those, they think that you lose a lot of energy from the generation all the way to the load. And actually, that's not the case. The efficiency, as far as heating and loss of energy, is not a big issue for transmission or distribution. So to answer the question, I would say observability. It's in some situations on the grid, it's like driving down the road with a muddy windshield or a dirty windshield, or in a rainstorm, you can't see very far ahead of you. And so the ability to know what's going on in real time, as well as after the fact, and be able to do forensic analysis, is just missing in certain parts of the system. Well, when I worked at TVA, which is a wholesaler, the amount of information that they have at the interstate highway level, if you will, the bulk power system level, it's just completely different than what's afforded to folks at the local level, the distribution level. They haven't had to make those investments. They haven't really needed that level of observability, but that's changing as the grid evolves and introduce new technologies and new capabilities. Well, I'm going to sound like a broken record, but observability and the data necessary to fortify those decisions. One of the, I think, a different perspective, and most people don't know this, that utility engineers are able to transform the physical infrastructure into math, into a mathematical model. And that mathematical model works very well when things are going smoothly, when things are normal. But when things are not normal, or when the situation on the grid is different from how they modeled it in the first place, the direction of the power flow, or dynamic changes in the load, say a big consumer comes online, that's not necessarily built into the normal model. And so that model has to be corrected or tuned with more data, with information. And the closer to real time that information is, the more accurate that information is the better that model can respond to what's going on. And that becomes more important as you're trying to move the power system in the right direction and keep it from, blacking out. Yeah, one of the examples that we've used to kind of jump a little bit ahead, I guess, with the grid metrics data is we have the capability at NREL to synthesize a model. So the utilities develop the model based on what kind of conductor they use, how long the conductor is, and they convert that information into a mathematical model. NREL has the capability to observe that model using just GIS tools and develop a fairly accurate synthetic model. It's not perfect. One of the things that we've been able to do, though, is to take disturbance information from the grid metrics system and essentially test the model. Did the model respond the way there was reality from the grid metrics data? And then tune it just a little bit to make it closer to the utilities model. This allows us to do research and to do analysis without costing or involving the utility in a way that they're not ready to engage yet. It's more of a perspective type of an effort. We're also, that approach can help them to see gaps in their model because things might have changed in their asset understanding, what conductors they've used, what spacing is involved, and we're able to say, your model doesn't match our synthetic model in a significant way. And we tested our model using actual measurements, and the utility can go, oh, there's an improvement to be made here. There's a lot of different things that the data can do for utilities, researchers, and the public in general to improve the efficiencies. The thing to remember is that the grid metrics data is a bottom-up approach to information. Like I said, the high-speed, interstate highway element of the grid, the bulk power system, it has measurement systems in place because of its function to move large chunks of power. It's like commercial, it's like train systems, and so it has those systems, but it has no understanding of what's going on at the distribution level. And many of the distribution systems may only have measurements at the terminals of their circuits. So at the substation where they receive power from the bulk power system, here's what's incoming, and then meters at your home or at the business that says here's what's consumed. Well, there's a long street, to kind of use my analogy, that's between those two, and it may be branched, it might be looped, in different configurations. They don't know what's going on in between. And so if there is a line down or a tree slap that's causing that could result in an outage later, or if there is an unusual load on that circuit, like a tier 3 electric vehicle charger or a solar connection, which might be causing the voltage to go high or the voltage to go low, they can't see that because they don't have measures on that line. So this information can help them to be a more reliable provider, a more responsive provider, and can reduce their cost of maintenance and response to events like outages. It's kind of a game changer at the distribution level. Yeah. Well, one of the most dramatic examples that most folks are aware of are the fires in California, and those affected high tension wires for the most part. And the response was policy that that created this public safety power shutoff. And so when there is a risk or a threat of fire, the utilities have the opportunity or the flexibility maybe to shut off power, effectively create blackouts, so that the fire itself is not complicated by down power lines. And so the fire burns through, causes down power lines, which cause, it grows the threat of the risk. At the distribution level, you have the same sorts of issues. You can have down power lines due to fire, due to accidents when hitting a pole, and without the awareness or observability between those 2 points, the utility can know there's an outage, but they won't know exactly where it is. So the response time is a person in a truck driving the circuit, looking for a down pole or an accident, or coordinating with local law enforcement to see where there might have been an accident. If you've looked at an outage management system online, you can type in your utility and outages, and many utilities have these outage management systems. All of those are based on a digital meter that's at your home, and say, okay, well, Eric's out of power, and so we know he's out of power, and his neighbor, she's out of power, and so they kind of bottom up and get a sense of where the outage, the root cause is, what pole is down, or what line is cut, or that sort of a thing. And so it takes a lot of computing power to do that, and it still requires eyes on the ground to see where that might occur. Now, with a system like this, you have a better sense of the actual location, because these sensors are on the line itself. And if you think about it, my example is someone driving the line. Well, in most cities, there is no line to drive because the conductor's underground. And if there's an event, there's a cut in or a failure of a splice or something like that that's beneath the ground, you can't observe it. So it becomes even more complicated. So a system like this would help identify it even more, could be even more valuable. I've been working in the power system business for about 35 years, and I've watched some of these questions. It's like, well, we could do this if we only had this information. And so we're not necessarily talking about the suite of products that GridMetrics has right now, but there's a second product that NREL worked with GridMetrics to develop that's even more robust than the measures that are on the circuit now, that can provide higher resolution and more detailed accuracy, that gets really deep into the nerd math on things that you can see that I haven't even begun to talk about. And those applications are truly exciting. You're talking about state estimation and phasor measurement and frequency measurement, and all these sorts of things that just make what little hair I have left stand up and wiggle around. It's really exciting. And so that's the short answer. When I was at TVA, we worked, one of my early projects, and we didn't talk about this earlier, one of my early projects was working with a manufacturer to develop a phasor measurement unit. And it measures, takes two of them, at least two of them, to measure very, very accurately, almost like an MRI machine. We talked a little bit about that, at one location, and compare it over high-speed communications at another location. If you do that, utilities estimate the state of the system with the models that I talked about. They don't know it, they estimate it. But if I have two of these devices, these phasor measurement units, I know what the power flow looks like. I measured it, and and I'm dating myself. It was novel at the time, and we in TVA and other utilities began to put these in. It was after the blackout in the early 2000s, And we were able to begin to see things that we hadn't seen before at the bulk power system level. This technology, this Grid Metrics 2.0, is that, but at the distribution level. And it's like, wow, do they need that at the distribution level? Not necessarily today, but as that system changes to host generation from distributed energy resources, from solar, from possibly vehicle to grid electric vehicles, and things like that, they're going to have a different paradigm, and they're going to need this kind of technology. And this kind of go back to the exciting part. Well, the consumer is all about cost and the expectation of high reliability. And this technology can help the utility to deliver those two services, if you will, to reduce cost, make them more responsive rather, to outages and to prevent outages in the first place, to know where they have needs to add investment, and they can evaluate those investments better because they have more visibility into what's going on the system, and help them prevent outages. No one likes to work from home or be watching a favorite sports event and they lose power. And so that's the utilities, or the consumer's bottom lines are those things. When we start talking about commercial and industrial, those two factors become more important because it's business related. They're in production. They've got freezers and lights, and they're trying to deliver product to customers. They don't want spoilage. They don't want to lose. If they're a restaurant, all these things depend on just the fundamental of the availability and reliability of the power. And so that's how this information can point to a better consumer experience. That's another benefit. It's not a benefit that's perceived or will be perceived everywhere yet, but as more of these green technologies seek to connect to the grid, they have a compounding or a stacking effect on the grid. They can affect the voltage, cause the voltage to rise, or when the sun sets for solar, they can cause the voltage to drop. Nobody wants high or low voltage. They don't want voltage jumping around. And so being able to measure that allows the utility to better to control the voltage, to do things with those systems to better manage the voltage, and things on their own equipment to better manage the voltage. So that's kind of an action. But that data, it also allows the utility to be more open, if you will, to more of that equipment connecting. There's a term that engineers use called hosting capacity, and there's a certain set of screens that the utilities use. And so at a certain point, they're like, well, we can't take any more. It's like a parking lot. I can't take any more cars because my parking lot's full. But they don't really know where all the parking spaces are. I was thinking about a little story. So there's a parking lot or a parking deck at my local airport that I just love to go to, because you drive in and it says there's parking spaces on floor 5, and you go to floor 5 and it says go to row 6, and drive down through there and there's a green light that says park here. I mean, of course I'm dating myself, but that's like, wow. Well, that type of an opportunity is what utilities can have with this level of information at the local level. They say, well, our former models that weren't informed by this level of information throughout the day wouldn't allow us to take more solar on this particular circuit. But with this level of information and the trending of it, they're able to see that, oh, okay, this will be fine. It won't have a significant impact, or we can do things to mitigate that impact this and this way and allow that to be connected, which makes the grid more green and helps everybody. Well, kind of the way I think about this, and I'll probably make half of the folks mad, and which is, it's like, is when I think about wireless technologies and 5G, they were designed to satisfy mobility requirement. I want to be able to communicate, or I want to be informed or entertained while I'm moving around, while I am in a relatively remote location. And so we've been trained in my engineering mind to accept that connection is not perfect. It's not 100%. It may have drops, may have areas where there is just no coverage, or the quality of it. You watch your phone and it drops from 5G to 4G to guess whatever number letters you got. And there's certain things you can't do when it gets to that space, but you may have emergency access and those kinds. But that's okay because it's a trade-off. But when I'm sitting here talking to you, I have a different expectation. This is business, or I'm sitting in front of my favorite, sports event on television. I expect high reliability. And while I may have a short hop to my server or my router over wireless, the backhaul of that, or the remainder of that, as Scott said, I'm not an IT guy, but is some type of wire, and that's obviously not wired necessarily, but coax, fiber, hybrid fiber coax, some sort, and that does deliver high reliability. And that's what grid metrics is built on. It's on that system. That's the expectation of communications reliability that the utilities have. They do depend on wireless technologies in certain cases because of the cost factor. It's very expensive to build out that extra infrastructure of fiber to the home, or fiber to the location, or some other sort of wired backbone. And so sometimes they depend on wireless technologies, but not for operations. We talked a little bit about, got a sensor at the substation and the delivery point, if you will, or the end point, or the where the power comes in, and then when the power goes out at the meter, there may be wireless radio at that point, but that's that cash register, if you will, doesn't need to report, or doesn't report in most cases in real time. It just needs to know how much power you use in an hour, how much power you used in a day, so that we can do billing. They don't often use that information for operations. When we're talking about operations, what we're really talking about is safety and reliability. So it has to be fast, and it has to be very accurate. It changes the dynamic of the reliance on the network itself. And the grid metrics system is built on that. We've talked a little bit about some of these things, but it is an enabling technology, allowing the distribution engineer, the distribution company, to become an operator. Sometimes you'll hear distribution system operator, but my experience with a wholesale company that operates the grid and manages power flow across multiple states, and is beholden to regulatory agencies like NERC and so forth for that reliability. That is what I think about when I think about an operator, an air traffic controller, if you will. But at the local level, operations has a different time constant. It's not real time. Having this quality of information allows them to transition to be more of a flight controller, an operator. They're like, well, we don't want to do that. As more of these advanced technologies come on the grid, DER, distributed energy resources, more local solar, energy storage, batteries, higher powered electric vehicle chargers, and things like that, and maybe things that we don't think about yet, they're going to need to change hats and become more of an operator to manage that dynamic nature of their system. One of the things that most people that aren't in this business, that don't sleep and eat it, don't realize is that the bulk power system is power goes every which way. But at the distribution level, for the most part, it's one way. It's a one-way street. Power flows downhill to power your toaster and television and whatever other loads you have in the Circle K down the street or whatever the C-store is. But generally, it doesn't flow back upstream. The push is to allow local generation to support local needs. That would help reliability, help green the grid, help reduce carbon, all these things. But the system doesn't, utilities will say, well, the system was never designed for that. Well, it's more complicated than that. You don't know what the system's operational capabilities are because you're like this. You have no observability. So this information will move them in that operational direction. Well, this one was kind of an eye-opener for me. It was one of those things that was in a meeting, and one of the good metrics folks was talking about DOCSIS. And I don't think about as a utility guy, I think about the cybersecurity of the grid because there are rules and regulations in place to guarantee that, so that no one can come in from the outside or a bad actor from the inside affect the operation of this equipment. But that is a completely different question in the broadband industry. They didn't design their system after the fact for security, which, in all honesty, that's how the power system did it. They didn't need security because security there was no communications. At best, you had a local operator. You had to worry about him or her. And even as you added communications to the station, it was obscure. It was some sort of communications that couldn't be accessed from the outside. And as it grew and became part of the internet, and security was layered on top of that. But in the broadband industry, they almost had to start with that because you couldn't have people stealing your favorite sports network or your favorite streaming channel or internet space. And so DOCSIS, and I don't know what all I don't know about that, but that is one of the most secure, fluent protocols that's available for high speed, low latency communications. And I never thought about that in 35 years of leveraging that foundation in a communication system. It's just baked in. So the utilities guys, how secure is this? That's going to be a question. Explaining that security is just fundamental to this industry, and you're going to ride this power system information on top of that. It's like being in a tank or a battleship. You're secure. You're fine. You don't have to worry about these attacks and these systems because of the layers that are around you and the layers you're embedded with. I'm doing a terrible job explaining that, but that's one of the issues. It's one of the main issues that I don't think the utility industry appreciates or understands about this technology. I think part of the question, or part of the answer, is what I just said about the security of this network. That's going to be a principal concern. If someone's watching this video and they haven't heard of the term NERC CIP, Critical Infrastructure Protection, from North American Electric Liability Corporation, those are the laws of the land with respect to cybersecurity for grid operators. How this technology wasn't designed because of NERC CIP, but meets those requirements. That's the extrapolation of my answer to that question. Helping them to understand that is essential. But what those utility executives will want first is this is a paradigm change. What's the business case for this? Helping them to understand what this technology obviates for them. They won't have to do this, or this, build out their own communication system. They won't have to manage the data, store the information. They might not have to manage the AI and the machine learning to do the forensics on the information. There's a host of things and services, information services, that GridMetrics has developed and will develop that can support the utility, that the utility won't have to invest in. Some utilities are very comfortable in leasing out certain services, construction, certain elements of engineering, but other things they're not as comfortable with because they're new, or they think that they need to keep that information in-house. So helping them understand that business case, the cost effectiveness of this solution versus owning the solution or operating the solution, or how there can be sort of a hybrid between the two. That's what the utility executive is going to need, in my experience. They're a very curious, intelligent lot. And they are very passionate about trying to help folks in the utility business. They see there's an opportunity, and they're, like I said, they're curious and innovative on taking this new to the utility business, new to the utility business information, and trying to develop solutions that can address those. I enjoy working with folks that are passionate and energetic and curious, and the folks at GridMetrics check all those boxes. But I came into the project, kind of halfway through, and tried to look around, and so. As I worked through the documents and what this was about, my aha moment was that we NREL, we're treating this as if it was an academic study, not the novel opportunity to change the paradigm for the distribution utilities. And, my utility hat on, I go, okay, wait a minute. We don't need to study this like we're studying this. We need to be doing this like this. And it's kind of hard to explain, but the opportunity that NREL had or took when they immersed me in this project as somebody with operational experience, I could see that, as we've just talked about, this broke open the observability question that the distribution utilities just can't afford, don't understand how much they need it, and really don't have a sense of the long-term capabilities, the long-term opportunities there. They just haven't had to sit down and deal with that yet. So in this project, we worked with a handful of utilities that saw that vision or recognized that vision and helped us to shape the project and lead it. And I think there's a huge opportunity to extend that, work with more utilities, and make this information available to other folks. And forgive me for relating a personal hero of mine. It's about 130 years ago. There was a 4-foot tall man that was a giant in power system engineering, Charles Steinmetz. He developed the mathematics that allows electrical engineers to turn a physical infrastructure into a model that they can put into their computer. And as I was saying earlier, that model largely is good for normal conditions and studying the situation as it is. When that situation changes, you need more information. Now, that in itself is the basis for state estimation. What is the state of the system at any given time? Where is the power flowing from point A to point B to C to D? At the grid level, that is essential for operation. At the distribution level, it's a relatively new concept that they haven't had to face. But they're beginning to talk about state estimation, distribution state estimation. And again, it's based on the models. The models at the distribution level, believe it or not, are more complicated than they are at the transmission level, because there's single phasing, because there's switching, because there's more concentration of loads. But with this measurement that we're talking about, you can jump past the reliance on complex math and do state measurement. That's a huge leapfrog. That's like going from airplane to Mars. Forget the moon. That's an aha moment. And why is that, again, why is that important? Because I want to put generation, I'm not talking about me specifically, but utilities and our strategic direction as a nation, we want to put generation at the local level. And as the shares of that generation increase, that information, that capability to measure the state is going to become more and more important. Right now, when I talk about reliability at the distribution level, it's like, are the lines down? Is the power on? But as I introduce more generation, reliability, the definition of reliability is going to change at the distribution level. When I say reliability to a grid operator, to a transmission operator, they might say, what kind? What kind of reliability? Do they mean that the frequency is in control? Is the voltage stable? These sorts of questions don't really mean anything at the distribution level yet. But when I have generation at the local level that may be doing this and this and this, they're going to need more information, because those characteristics of reliability are going to be part of their business. That's an aha moment that they haven't recognized. Most of them haven't recognized yet. I was just chatting with a friend, and she was telling me about some other opportunities, I'll say, and I explained that the things that I like to do are to help people to understand how technologies can meet their needs. In my experience, working at a utility, everybody, believe it or not, everybody's not an electrical engineer. Your boss is probably a lawyer or an accountant, but they make those decisions. When I talked earlier about the business case, they don't want to hear the technical issues. They want to know, okay, I trust you as an engineer to understand how this will help improve the things that I need to be, reliability and safety. Explain to me how this will help my business, how this will help my bottom line. Help me to translate that technology into my business needs. I enjoy doing that, jumping in the middle of folks that are brilliant scientists and engineers with technological solutions, and folks that have needs or gaps that they may not be able to explain, or they may not fully comprehend, or they may not expect yet, and matching those two together. And so that I came here for that, but that's where I have arrived. You know, that's in my career, and I really enjoy trying to do that. And this is an opportunity for me to insert my voice.